Hello everyone, my name is Jason Gregerson. In this video we're going to have a quick tutorial on numerical integration. Specifically we're going to program the left sum and midpoint methods for approximating a definite integral. We're also going to talk a little bit about establishing and then exploring an error bound for our midpoint approximation. So we'll start by looking at the left sum. Now of course before we want to dive right into our programming, we're going to remind ourselves what we're actually doing when we calculate a left sum approximation. Let's look at this example. I want to approximate the area under this curve, y equals f of x, from A to B. Now, we don't generally have a formula for the area under this curved line. So instead what we do is we break up this interval from A to B into many different subintervals, just like this. And then each one of those subintervals, for instance this one right here, we will create a little rectangle by taking the height of this rectangle to be the height at the left side of the interval, hence the left sum technique, and the width of this interval to be a small change in the x value, which I'm going to call delta x. It's saying this x value minus this x value. So that's a small change in x. So if I wanted to calculate the area of that one rectangle, it would be, once again, the height at this x value. I'll call that some x sub I value. It's some random x value along my interval from A to B. The height will be f of x sub I then, and the width will be delta x, whatever that is, and that should be the area of just this rectangle. Now, I'm going to do that for all of these rectangles from A to B, and then I'm going to add them up. Here's my notation for adding those all up. It's taking the sum of this product. And this is in general what I'm going to do for my left sum technique. Of course, there's a couple hidden details here. For instance, what are these specific values? How do I actually calculate what delta x is? Well, in general, I'm going to know a couple things. I'm going to know where I'm starting at. I'm going to have this a value, so I could maybe say I'm starting at a equals 1, and then I'll know my b value. So I'm maybe integrating from 1 over to 2, for instance. Now, delta x, the width of each one of these rectangles, is going to depend on how many intervals I have from A to B. If, for instance, I'm going to use 10 intervals, so I'm going to let n be the number of intervals, I'll say I'm going to have 10 in this case, then my delta x I should be able to calculate by taking the total length of this interval. So in other words, b minus a, in this case 2 minus 1 says I have an interval length of 1, and dividing by the number of intervals inside of this one big interval. So b minus a divided by n should give me my delta x value, how wide each interval is. Okay, let's start to do a little bit of programming now. So I'm going to go back into Mathematica, and I'm saying, okay, I am trying to find the area under some function from A to B using n intervals. So I'm going to know what my function is. We will use an example, the function x cubed plus 2x. So we have our function. I want to find the area under this curve from A equals 1 to B equals 2, and I'm going to use n equals 10 intervals. And then we said we have a way we can calculate what our delta x is. Our delta x should be b minus a divided by our n value. And the nice thing about Mathematica is I can take this cell now and run it and actually see what that delta x value is. And that makes sense. If I'm going from 1 to 2 and taking 10 steps to get there, each step should be 1/10. So I've calculated my delta x value. Now the next thing I'm going to need are all my xi's, all the endpoints to all my intervals along this path. And so how am I going to calculate those? Well, I can start out by saying I should know what the left side of the very first interval should be. I mean, I'm starting at a equals 1, so a should be that first point along the way. What about the next one? Well, if I started at a, and I took one step over to get to my next point, that must be a plus some delta x. So if I started at 1, for instance, I took a step over 1/10, I should be at 11/10. I'm going to look at the decimal. If I put a decimal value in, I should get a decimal value out. So I'll put a decimal value right there, and I will rerun this, and sure enough, I'm at 1.1. Now, what about the next endpoint, the next point along my interval? Well, if I start at A and now I take 2 steps over, that should give me the next endpoint. What about 3 steps? What about 4 steps? In general, if I took some number of steps over, I should get to that coordinate along my path. I could see all of these by building a little table where I'm going to let I go from 0 to n, for instance. And sure enough, now I have all the different points along my interval. Now, of course, what I want to do is I want to calculate the height at these different points. So that would be having my function evaluated at these x values, at these little x sub i's. That should give me the height at each of these endpoints. And then I want to take that times my delta x. So times my delta x value. And that should represent the area. Now, the only one thing I have to account for here is that I actually don't want that last one. So if I go back to my little drawing here, I would add up all these little rectangles. But I actually don't want this last rectangle because that's going outside of my interval. So I don't want that value of 2 at the end. So instead of looking at all those from 0 to n, I'll go to n minus 1. And instead of just listing all these area values, I actually want to add them all up. So I will use the sum command instead of the table to actually add up those values. And then I had this value of 6.3075. But is that value any good? It's hard to tell at this point. Well, because I have a nice easy function, I can actually calculate the exact value by just integrating. I could integrate from a to b my function and see the exact area of that curve. I see that it's 6.75. So I was in the neighborhood with my approximation of 6.3, but it wasn't too close, and that's probably because I only took 10 steps. I can improve that, however, if maybe I want to take 100 steps. I'll rerun this cell, rerun my approximation, and sure enough, I'm much, much closer. I could get even closer if I want to take, for instance, 10,000 steps. And now I can quickly do that in Mathematica, and sure enough, I'm getting very close now. So that's the left sum approximation. What about the midpoint approximation? Well, it's the same basic idea, if we go back to our picture, except now, instead of taking the height at the left side of my interval, I want to take the height at the middle. Right there. That's going to be the height of this rectangle. So how am I going to calculate those values? Well, let's look back at that table we used earlier. I'm going to grab this and just copy it and paste it right in here. I want to look back at those table values that I used before. Oh, except I only want to look at that for n equals 10, like I did originally. All right, now I see those 10 different left side endpoints. Now, what do I want? I really don't want to evaluate my function at 1 and 1.1, 1.2 anymore. Instead, I want to evaluate my function somewhere between 1 and 1.1. So that's like taking my 1 value and adding half of a delta x. So in other words, I could take this thing and add my delta x divided by 2. And if I just put that in there and rerun it, now I have the number in between 1 and 1.1, the number in between 1.1 and 1.2. So now I have all of these in between values. So these look to be the values I want to evaluate my function at. Now that's one way to get it. Another way to actually get these midpoint values would be to take a plus I times delta x, which would be the left endpoint, and then I could add that to a plus I plus 1 delta x. That would give me the right side of each interval. I could actually average those two values to find this middle point value as well. That would be the general formula. This would be a simplified version that I can program a little easier. So I want to take the height at all these points, times it by the width, which is my delta x. And then instead of just listing them, I want to add them up. And this should be my midpoint approximation. Notice that I'm still only using n equals 10 intervals, and my answer is already very close to the exact value. So it's a much improved value here. Now, the only problem is, now, what if I want to change my value of n, or change my interval, change my function, for instance? Well, I could keep going back up to this top cell, editing these values, rerunning this cell, and coming back down here and rerun this cell, but that seems a little tedious, and I could lose some values somewhere in the way, especially if I have to scroll up and down to a large document. So instead, I'm going to create a program that will take certain inputs and do this midpoint calculation for me. I'm going to call my function mid. Seems appropriate. Now, what are the variables for my function? Well, these are the things I should know in general to do my midpoint approximation. In general, I want to do this integral. Integrate some function from a to b. I need to know how many steps I'm going to take. So those are going to be the variables of this midpoint function now. I'm going to need to know the function, whatever that's going to be. I'm going to integrate that function from a to b, and I'm going to use some number of intervals. Now, right here I have all these values and I should be ready to go. The only problem is the way I program mid, I use these delta x's. But delta x depends on a and b and n. So I need to include not just the delta x, but actually the form of delta x in here. So real quick, what I'm going to do is I'm just going to copy that expression and get rid of all my delta x's in here and put in what it's equal to, which is the b minus a over n. That way everything in my program is in terms of f, a, b, and n. Now, the only other thing I also have to remember is use colon equal when I'm defining this function. Now I'm going to run this function, and now I can call this function. So I can say mid of the function I used. I did it from 1 to 2, and I used 10 intervals. And once again, I got to put a decimal in to get a decimal out, and there's that same value I had before. But not only that, I could say create a new function. For instance, g of x equals sine of x. And I could approximate the area under that function from maybe 0 to pi using 10 intervals. I get a value of 2.0825. So now it's very easy for me to, on the fly, do new midpoint approximations. So now I programmed left, I programmed mid. Now I'm going to talk about the error in my approximations. Because right now, if I look at this, here's my approximation, but I don't know if that's any good. I don't know if the real answer is 2 or if it's 4. I don't know how close I am to the real answer. Well, we learned that the error in a midpoint approximation is always less than or equal to this expression, so long as k, that k value in there, is greater than or equal to the second derivative of my function for all x on the interval from a to b. Alright, so what does this mean? Well, it says whatever the error is in this approximation, it has to be less than this thing. Well, let's calculate that thing. I have that b minus a. So for instance, in my last approximation, where I was approximating sine from 0 to pi, the b value was pi, and my a value is 0. That's my interval width here. So I know those values, and it looks like I'm cubing that. And that's divided by 24 times n squared, but in this case I just used 10 intervals, so that's 10 squared. So I know all those values. The only thing I don't know is this value of k. But once I figure that out, I could run this cell and figure out what the maximum value of the error was. I would have my error bound. So what about k? Well, it says here that k has to be greater than or equal to the second derivative for all values of that second derivative on the interval from a to b. So let's take a look at that second derivative. The second derivative, and I'm using g of x here, that's the function I'm actually trying to integrate. So I will look at the second derivative of that. The second derivative is negative sine of x. Well, let's take a look at that function. I could plot that function, for instance, over my interval from 0 to pi. Remember, that's the only area now that I care about this second derivative. Okay. Now notice that k has to be greater than or equal to the absolute value of the second derivative. So I have negative values throughout this interval. So if I want to see the absolute value of the second derivative, I can use the command abs for absolute value. Now take the absolute value of it. And so the value I'm choosing for k has to be bigger than any other value for this function on this interval. Well, it looks like k has my second derivative has a maximum value of 1 that occurs at pi over 2. I saw that my second derivative was negative sine of x, and I know that that has a maximum value of magnitude of 1 at pi over 2. So I know that if I let k equal 1, it will be bigger than any other value, bigger than or greater than or equal to any other value of the second derivative on this interval. So I'm going to let k equal 1. Now in general, I was able to look at this picture here, and also my understanding of that trig function, I knew what the maximum value was. In general, however, you might have to do some optimization to actually find that maximum value. All right, I have my value of k though. I evaluate this, and this is my error bound. This tells me that this is my approximation to that correct area, and I know that that answer, the real answer, is plus or minus 0.0129 of this value. Let's check that real quick here. Once again, I can calculate the exact value in this case here. So I can actually calculate the exact value of the area under sign by integrating from 0 to pi my sine function and get a value of 2. So that's the exact value. I could subtract my approximate value. That's my approximate value. And so if I subtract these two, I'll get the error. And once again, decimal in, decimal out. So it looks like my exact error was 0.008, which is less in magnitude to my error bound. So sure enough, the real answer was within this error bound. So what have we done so far? We've programmed left, we've programmed mid right here, and we talked about how we can establish an error bound for our approximations. Here is our formula for the error bound for mid. We knew what b, a, n were. The only thing we had to figure out was k, and we could actually explore what that second derivative function looked like and find the maximum value of that second derivative on the interval to find that value for k. And then we could compare our answer to the exact solution. All right, that concludes this video. Thank you.